How are you, my students? Today we are going to continue with the topic linear motion. We are still in linear motion, and today we are going to define our next term. So far we have defined the following. We have defined distance. We've also defined displacement. We've also defined what speed is. We've also defined velocity, and we have acceleration as the last term in this topic. So we are going to talk about acceleration today. Acceleration. And before we go to acceleration, I would like to review what we covered previously, that is in velocity. The previous lesson we were looking at velocity. Just to do a reminder, we said velocity is the change in displacement, per unit time, change in displacement per unit time, whereby we say therefore if we use v to represent velocity, therefore velocity v is equal to displacement per unit time. S, which stands for displacement, then t for time. Velocity is the change in displacement per unit time. And then we said velocity is a vector quantity. Velocity is a vector quantity. And we said that whenever we are calculating velocity, we consider both the size and also the direction. So it is a vector quantity. Then again we said if there is equal change in displacement, or if there is same or equal change in displacement, that is per equal time interval, change in displacement, if there is equal change in displacement per equal time interval, no matter how the intervals may be, we say therefore that the body is moving at a constant or uniform velocity. The body is moving at a constant or uniform velocity. That is, if there is equal change in displacement per equal time interval, no matter how small the time interval may be, then the body is seen to be moving at a constant or uniform velocity. If that is not the case, then we say that the body is moving at non-uniform velocity. If the velocity is not uniform, if it's not this case, then we say that it is moving with a non-uniform velocity. Then we also need to know that if we have velocity at a particular time, velocity at a particular time is referred to as instantaneous velocity. Is referred to as instant, from the word instantaneous velocity. That is velocity at a particular time. We refer to it as instantaneous velocity. Velocity at a certain point at a particular time is what we are referring to as instantaneous velocity. So today we are going to move on to our last term, that is acceleration. And by the end of this lesson, you will be in a position to define acceleration. Define acceleration. Again, you will be also in a position to get to calculate any question involving the numerical, that is the numerical calculations. That is for acceleration. Those are the things that we should be able to do by the end of the lesson. So I want us to start by the definition of acceleration. When we talk of acceleration, it simply refers to the change in velocity per unit time. It refers to change in velocity per unit time. Change in velocity per unit time. Or we can say it is the rate of change in velocity. Simply the rate of change in velocity. That is simply what we refer to as acceleration. The change in velocity per unit time or rate of change in velocity. So therefore, we say that acceleration is equal to change in velocity the velocity per unit time. So divided by the time taken. Change in velocity per unit time. That's how we define acceleration, the change in velocity per unit time. And therefore, we also need to know that acceleration is denoted by a small letter a. Acceleration, we denote acceleration is denoted by a small letter a. This is the symbol for acceleration. It is not the SI unit. We can even write it here. So we have A for acceleration, a small letter A. And therefore, we can go ahead and therefore say, when we want to get the change in velocity, will simply be given by the final velocity minus the initial velocity. We'll have the final velocity. For us to have the change, we have the final and the initial. So the final velocity minus the initial velocity. That's what will give us the change in velocity. And therefore, we can go ahead and say that acceleration will therefore be equal to change in velocity, which is final velocity minus the initial velocity. Final velocity, we subtract the initial velocity, we divide by the time taken. This one will give us the acceleration. So acceleration is the rate of change of velocity, or simply the final velocity minus the initial velocity divided by the time taken. And therefore, we also need to know the symbol that we use to denote the final velocity. The final velocity, we denote it using a capital letter V. We use V. Then for the initial velocity, we use a small letter U. So ensure that it has the tail. And as we know, for time, the time, we use a small letter T for time. And therefore, from this formula, we are going to have that acceleration, therefore, acceleration A therefore will be equal to final velocity V minus the initial velocity divided by the time taken. So this is our acceleration, the change in velocity per unit time, or the rate of change in velocity. So we have the final velocity minus the initial velocity divided by the time taken. That's what we have for acceleration. Therefore, we can also continue and say, now that we know that acceleration A is change in velocity, that is V minus U all over T, we also need to get from this, we will be able to know whether acceleration is a scalar quantity or a vector quantity. We know that this change in velocity, the velocity is a vector quantity. So we are having a vector quantity, and we know that time is a scalar quantity. So a vector quantity divided by a scalar quantity, we also get a vector quantity. And therefore we say that acceleration is a vector quantity. Acceleration is a vector quantity, meaning that it shows both direction and magnitude. Both the direction and magnitude. So that's acceleration, change in velocity per unit time. Then we have seen that acceleration is a vector quantity. We also need to get the SI unit. What will be the SI unit of acceleration? The SI unit of acceleration. So we get the SI unit from the formula, whereby we are saying acceleration is the change in velocity, v minus u, divided by the time taken. And we know that v minus u, the unit for velocity, the SI unit, we said is meters per second. And then the SI unit of time is seconds. So when we divide meters per second, divide by the seconds, we are going to have meters per seconds divided by the seconds. This is always over 1, a whole number. So we'll have meters per second multiplied by 1 over second. So we are going to end up getting meters per second square. And therefore the SI unit is meters per square second. So the SI unit of acceleration is meter per square second. Meters per square second, which we write it as meters per square second, or you can write it as meters per square second this way, meters per square second. So the SI unit of acceleration is meters per square second, which you can write in this form or in the other form, or the full ones, that is meter per square second. So that's what we have for acceleration. And always note, whenever you want to get the SI unit and you have a formula, you need to get the SI unit for the numerator, that is the change in velocity, which is meters per second, and then the SI unit of the denominator, that is time, which is seconds. And when you divide, you are going to get that the SI unit of acceleration is meters per square second. Now, again with acceleration, let's have the formula here still. Acceleration, we've said, is the rate of change of velocity. Now, if we have a body moving with a constant velocity, if the velocity is not changing, for a body moving at a constant, velocity, that means that the velocity is not changing. The initial velocity is equal to the final velocity. That is, the final velocity is equal to the initial velocity. Therefore, it means that the acceleration, the acceleration for such a body is 0. The acceleration is 0. This is since because, for example, if we take our initial velocity to be 20 meters per second, that body is moving at a constant velocity, and therefore the final velocity again is also 20 meters per second. The final velocity is again 20 meters per second. It means that acceleration will be final velocity minus the initial velocity divided by the time taken. So we are going to have the final velocity 20 meters per second minus the 20 meters per second. We divide by the time taken. Time taken can be 2 seconds, it can be whatever the number of seconds. So we are going to have it as, that is for a body moving at a constant velocity. Therefore, it means that acceleration will be 0 meters per second. That is the change divided by the time taken. Any number, a 0 divided by any number is equal to 0. And therefore, it means that the acceleration will be 0 meters per square second. So for a body moving at a constant velocity, that is, final velocity is equal to the initial velocity, the acceleration of such a body is equal to 0. The acceleration of such a body is equal to 0 because when you get to subtract, you get 0 over a number. T can be any number that is which is not less than 1, and we are going to have that our acceleration therefore is 0 meters per square seconds. Now, we also have the acceleration at a certain point. Acceleration at an instant. Acceleration at an instant or at a certain point, at a particular point, is referred to as instantaneous acceleration. Acceleration at an instant is referred to as instantaneous. Instantaneous is referred to as instantaneous acceleration. That is acceleration at a particular or at an instant is referred to as instantaneous acceleration. Then we also have another case whereby we can have a body whose velocity is changing uniformly with time. That is at the same equal time interval. For a body whose velocity changes equally at the same time interval, at equal or at the same time interval. For such a body, maybe I can give an example, then we say the motion, or we say what we call that acceleration. That is for a body whose velocity changes equally at the same time interval. Changes equally at the same time interval. For example, maybe I can give an example of a table whereby we have acceleration, we have velocity and time. Let's say here we have the velocity in meters per second. Then here we have time in seconds. Let's say we have 0, 10, 20 meters per second, 30, 40, even up to 50. And then here we have the time here is 0, then it goes to 2, 4, 6, 8, 10. Now I want us to look at to see the change in velocity. How the velocity is changing from 0 to 10. Here we have the change as 10. Here from 10 to 20, the change is final minus the initial, which is again 10. Here the change is again 10. 40 minus 30, we also have 10. Again here we have 10. Then if we look at the time, how the time is changing, we'll have again 2 minus 0, 2, 4 minus 2. So we have 2 again and 2 there. So we are saying that the body whose velocity changes equally, the velocity is changing equally at the same time interval. You can see the time interval changing equally at the same interval. We say that the body is moving at a uniform acceleration. This is what we refer to as uniform acceleration. Uniform acceleration. And we can calculate that acceleration, whereby acceleration we've said is the rate of change in velocity. So at any point, for example, at this point, we are going to have the change in velocity is 10 minus 0, which is 10 meters per second, and the time is 2 seconds. And therefore, our acceleration is 5 meters per square seconds. If you calculate on this other interval, it will still be the same, because at every point, we have 10 divided by 2, 10 divided by 2. So our uniform acceleration, this uniform acceleration is equal to 5 meters per square seconds. So we say that for a body whose velocity changes equally at the same time interval, no matter how the interval may be, no matter how small or how big the interval may be, that acceleration is referred to as uniform. We can also talk of uniform or constant acceleration. It is referred to as uniform or constant acceleration. Then again, We can also have a body. We can also have another body whose, for a body whose velocity decreases with time, whose velocity decreases with time, for a body whose velocity decreases with time. For example, initial velocity, let's say, was 80 meters per second, and then as time continues, the final velocity drops even up to 20 meters per second. If we have a body whose velocity is decreasing with time, as the time increases, the velocity is decreasing, we say that that body is decelerating. The body is decelerating. From the one acceleration, now we have deceleration. So we say that there is what we refer to as deceleration or retardation. We talk of deceleration or retardation. And we can calculate it from this. Let us say that the time taken here was 5 seconds. 5 seconds. So we are going to have, therefore, we need to calculate that acceleration. And now if the acceleration will be a negative, we'll conclude that that body is retarding or it is decelerating. So we are going to have our acceleration as v, final velocity minus the initial velocity, all over time taken. Our final velocity is 20 meters per second. Our initial velocity is 80 meters per second, divided by the time taken, which is 5 seconds. So we are going to have 20 minus 80, which is negative 60 meters per second. We divide by 5 seconds. So when we divide this, you can see we have a negative there. Negative 60 divided by 5, we are going to get our acceleration, therefore, to be negative 12 meters per square second. This negative, the negative shows that the velocity of the body decreases with time. The velocity of the body decreases with time. And therefore this negative shows that it indicates a deceleration, or simply what we are calling the retardation. It represents it indicates that it is a retardation or it is a deceleration. And therefore, if you are trying to calculate the acceleration, therefore it means that the acceleration will be equal to negative 12 meters per square second. And this negative stands for deceleration or the retardation. And therefore, if you are trying to calculate what is the retardation therefore is equal to 12 meters per square seconds, because the negative is being cut and formed by the one retardation, meaning that the velocity of the body is decreasing with time. So the key things here that we need to note, we've said one, for a body that is whose velocity is changing uniformly, that is, the velocity changes equally at equal intervals of time, we've seen that we have this motion being referred to as the body is moving at a constant or uniform velocity. And we have also seen that if the velocity of the body is decreasing with time, velocity decreasing with time, then the body is said to be at deceleration. The body is decelerating, or simply we have the body retarding. There is a retardation, retarding. So that's what we have, velocity changing equally with time. We have constant or uniform velocity. Then the velocity decreasing with time, we have the deceleration or the retardation, or the body is seen to be decelerating or it is retarding. So the negative in this, negative acceleration is what we are referring to as the retardation. I want us to do an example or some examples on this. Do some examples. I want us to do an example or some examples. So examples. Number one, the velocity of a body increases from 72 kilometers per hour to 144 kilometers per hour in 10 seconds. Calculate its acceleration. So I want us to calculate the acceleration. We are told that the velocity of a body increases from. So when you hear of the word from, it means that this is the initial velocity. It increases from 72 kilometers per hour to a velocity of 144 kilometers per hour, and the time is in 10 seconds. Calculate its acceleration. So the first thing is to analyze the equation. You should know the values that are given. So we have the first one, increases from 72 kilometers per hour. So our initial velocity u is equal to 72 kilometers per hour. Then it increases to 144 kilometers per hour. So our final velocity v is 144 kilometers per hour in 10 seconds. So our time is 10 seconds. And we want to calculate the acceleration. And therefore, we need to consider the formula from the definition of acceleration, whereby acceleration is final velocity minus the initial velocity, final velocity minus the initial velocity all over the time taken. And as you can see, we have kilometers per hour, and here we have seconds. And we are told to calculate the acceleration. And we also need to get the acceleration in the SI unit, which is meters per square seconds. And therefore, we have to change the kilometers per hour into meters per second. So we start by changing the 72 kilometers per hour into meters per second. So this one, we change first kilometers into meters, then we change the hours into seconds. So we are going to have, we know that 1,000 meters is an equivalent of 1 kilometer. So we have the 72 kilometers. We want to know how many meters are there. So you come and cross multiply, you get 1,000 meters multiplied by 72 kilometers divided by 1 kilometer. So we are going to have these 72,000 meters. Then we convert again. We know that 3,600 seconds is an equivalent of 1 hour. So we have therefore 72,000 meters per 3,600 seconds. And therefore this means it is 72,000 meters we divide by 3,600 seconds. And we are going to get this as we can cancel this by this is 2. So we are going to get 20 meters per second. So that is the velocity, that is the initial velocity. We also calculate the final velocity in meters per second, the final velocity. So we have 144 kilometers per hour, 2 meters per second. So again, 1,000 meters is an equivalent of 1 kilometer. What about 144 kilometers will be an equivalent of how many meters? So we have 144 kilometers. We multiply by 1,000 meters. We divide by 1 kilometer. So we end up getting 144,000 meters. So we'll have, therefore, it is 144,000 meters per hour. And we have said that 3,600 seconds is an equivalent of 1 hour. So 1 hour is an equivalent of 3,600 seconds. So this means it is 144,000 meters divided by 3,600 seconds. So if we cancel these two, now we have 1440, that is 1,440 divided by 36, and we end up getting 40 meters per second. And therefore, we can calculate the acceleration because we have the initial velocity, which is 20 meters per second. We have the final velocity, which is 40 meters per second, and we have the time taken. So we are going to have acceleration as the final velocity, which is 40 meters per second, minus the initial velocity here, that is 20 meters per second. We divide by the time taken, which is 10 seconds. So we are going to have 40 minus 20, which is 20 meters per second. We divide by 10 seconds. And we end up getting 20 divided by 10, which is 2 meters per square seconds. And this is the acceleration. So our acceleration is 2 meters per square seconds. As we said, you can see that the final velocity is greater than the initial velocity, meaning that there is an acceleration. The body is accelerating, which is the opposite of deceleration. So our acceleration is 2 meters per square seconds. I want us to do an example 2. Example 2 on acceleration again. Question number 2. We have a car. A car is brought to rest. A car is brought to rest from 180 kilometers per hour in 20 seconds. And the question is, what is its retardation? What is its retardation? What is its retardation? So that's what we have. A car is brought to rest from 180 kilometers per hour in 20 seconds. So we have this car initially traveling at a velocity of 180 kilometers per hour, and then it is brought to rest. When it is brought to rest, it simply means that the velocity at rest is 0 meters per second. So initially it is moving from, the velocity is 180. So the initial velocity is 180 kilometers per hour, and then it is brought to rest. Whenever you hear of rest, it means that the velocity is 0 meters per second, or maybe 0 kilometers per hour. So we have therefore the final velocity, because the car is brought to rest, then is 0 meters per second. And therefore, and it takes, the time taken for that is 20 seconds. So the question is asking us, what is its retardation? And we know when we want to calculate the retardation, we need to get the acceleration, because we said a negative acceleration gives us the retardation. So we need to calculate the acceleration so that we can get that retardation. So therefore, our acceleration from the definition is the rate of change in velocity. So we need to get the final velocity, which is already here 0 meters per second. Initial velocity, we need to convert the 180 kilometers per hour into meters per second. So we have the 180 kilometers per hour to meters per second. We know that 1,000 meters is an equivalent of 1 kilometer. So what about 180 kilometers? So we are going to have 180 kilometers. We multiply by 1,000 meters. We divide by 1 kilometer. So the kilometers will cancel, and we get that our initial velocity therefore is 180,000 meters. That is the meters per not meters per second. This is the distance, that is 180,000 meters. That is the distance. Then it is per hour. So, and 1 hour is an equivalent of 3,600 seconds, and therefore our initial velocity will be 180,000 meters per 3,600 seconds. So we are going to have 180 divided by 36, that is 5, then that's 0. So we have 50 meters per second. So our initial velocity is 50 meters per second, and our final velocity is 0 meters per second. And therefore, our acceleration will be the final velocity, 0 meters per second, minus the initial velocity, which is 50 meters per second, divided by the time taken. And our time taken is 20 seconds. That's the time taken, 20 seconds. So we have 0 minus 50, which is negative 50 meters per second. We divide by 20 seconds. So negative 50 divided by 20, we have it as negative 2.5. Negative 50 divided by 20. So we are going to have our acceleration as negative 50 meters per second divided by 20 seconds. So we can cancel the zeros. Negative 5 divided by 2, we get negative 2.5 meters per square seconds. This is now the acceleration. The acceleration is negative 2.5 meters per square seconds. And this negative is representing the retardation. And therefore, our retardation therefore will be equal to 2.5 meters per square seconds. So that gives us the retardation. This negative is represented by this one, retardation. So from this, a negative acceleration. A negative acceleration is what we are calling the retardation. So if you had been asked to calculate the acceleration is negative 2.5 meters per square seconds. But if it is not the retardation, it is 2.5 meters per square seconds. Lastly, the last example, question number 3. A bus starts from rest and attains, and its velocity increases to 40 meters per second in 5 seconds. In 5 seconds, calculate the acceleration. Calculate the acceleration of the bus. Calculate the acceleration of the bus. So here we have a bus starting from rest, and its velocity increases to 40 meters per second in 5 seconds. Calculate the acceleration of the bus. So in this case, we are told that this body, that is the bus, is starting from rest. So the initial velocity from rest, so the initial velocity, if the body is at rest, the initial or the velocity at rest is 0. So we have 0 meters per second, and it attains a velocity of 40 meters per second. So the final velocity is 40 meters per second, and the time taken for that is 5 seconds. So the question is, calculate the acceleration of the bus. the acceleration of the bus, and therefore acceleration is the rate of change in velocity. So we have the final velocity as 40 meters per second. We have the initial velocity as 0 meters per second, and the time taken is 5 seconds. So we have 40 minus 0, which is 40 meters per second. We divide by 5 seconds, and we end up getting 40 divided by 5, which is 8 meters per square seconds. And therefore, the acceleration of the bus is 8 meters per square seconds. That will be the acceleration. Now, from the terms that we have defined, so far, we can now be able to group them. We can be able to group those terms into either scalar or vector quantities. We started with distance, and distance we said is a scalar quantity. Then we had displacement, which is a vector quantity. Displacement is a vector quantity. Then we have speed, which is a scalar quantity. We have velocity, which is a vector quantity. And we finally have acceleration, which is also a vector quantity. So these are the terms that we have been defining. So distance, length between 2 points. Then we say displacement is distance in a specified direction. Speed is the distance per unit time, or the distance covered per unit time. Then velocity is the change in displacement per unit time. And finally, acceleration is the rate of change of velocity. I'd like to give you an exercise. Question number 1. A body is meant to change its velocity from 20 meters per second to 30 meters per second in 0.01 seconds. What is the acceleration produced? Number 2, a particle moving with a velocity of 2.0 times 10 power 5 meters per second is brought to rest in 2 times 10 power negative 2 seconds. What is the retardation of the particle? So ensure you do those 2 questions to be well conversant with the sum topic, and thank you very much for being my good student.